Before we get going on the math, let's just remember what refraction is. Refraction is the change in light as it passes from one medium to another. So here we've got a laser shooting at the boundary between air and water. And notice that it doesn't continue in a straight line, it bends. So the direction of that light is changing as it's changing mediums. That's called refraction. Some other things go along with refraction. Notice that these bright spots, they are going to be the crests, and the dark spots are going to be the troughs. And we've got a certain wavelength here. But then when we move into the new medium, into the water, that wavelength is no longer the same. It's a little bit shorter. Now we also have a reflected bit of light over here. So some of this light is going into the new medium. That's called transmission. And some of the light is reflecting off of it. That's reflection. So this is the refracted or transmitted light, and this is the reflected light. We're going to ignore the reflected part for now and concentrate on the refracted part. So let's get into the math. So as waves change mediums, several things change about them. Their speed changes, their wavelength changes, but the thing that does not change is their frequency. The same number of waves is reaching that boundary between the two mediums per second, and that's what frequency is. Frequency is waves per second. So when the wavelength gets smaller and the waves are bunching up together, it seems like there would be more waves per second happening, but their speed is also decreasing. And so since the speed is decreasing just the right amount, they're going to have the same frequency as they did before. So when a wave approaches a boundary, it can approach the boundary just straight on, and then wavelength and speed will change, but it could also approach a boundary at an angle. And when that happens, the angle will also change in the new medium. And so when you put a straw into a glass of water at an angle like this, the reason that it bends is because of refraction. So that angle of the light that you're seeing is changing as well. So frequency stays the same. Speed, faster in a rare medium. So there's two mediums, two descriptors for mediums, rare and dense. Rare means not very difficult to move, something thin. And then dense is obviously something heavier, something more difficult to move. So in a rare medium, things move faster. And in a dense medium, waves move slower. Now, we're talking specifically about light, really. Mechanical waves actually travel different ways. So when you're listening to sound underwater, it's actually going to travel faster than through air because of the way that the particles have to interact with each other for a sound wave to travel. When sound travels through water, water molecules are much closer together than air molecules are, and so the less movement needs to happen with the water molecules in order to pass on that energy to the next set of molecules. And so try this if you'd like. When next time you're at the beach, if ever that happens, you can pick up two rocks, clack them together while you're above water. They'll sound a certain way, and then go underwater, ears and everything, and then clack them together underwater as well, and you'll notice that there's a sound difference. So, in a rare medium, light waves move faster. In a dense medium, they move slower. And now wavelength. So, wavelength is going to be longer in a rare medium. Now we're also going to be able to do some calculations with these things. So yes, waves speed up when they move from a dense medium to a rare medium, but how much do they speed up? How do we tell that? So that's the thing that we're going to be working on from here on. So let's just take a quick look at a diagram. So this is a boundary between a rare medium and a dense medium. Let's say that this one is rare and this one is dense. And then we're going to have some waves. Let me grab. We're going to have some waves moving toward that boundary. So here's a wave front number 1, wave front number 2, wave front number 3, etc. moving this way. And when they reach the boundary between the rare and the dense, they're going to kind of stack up because it's more difficult to move the molecules in the dense medium, or waves move slower through the dense medium. So here's how it looks. The wave fronts get closer together because they've slowed down. And now they're traveling this way as well. So when this first wave front reaches the boundary, it slows down. But the next one in line is still moving just as fast as it was before, and so it catches up to the first one a little bit. And same thing with the next one. And so they're catching up to each other at this boundary, and that's why they are all stacked up on the other side. And so you can see that the wavelength from here to here, crest to crest, is much smaller than this wavelength. Okay, so the speed has gotten slower, and the wavelength has gotten smaller. This is just going straight on. And so we can take a look at what's happening mathematically using V equals F lambda. Okay, but we need to first of all notice that frequency 1 in the rare medium is the same thing as frequency number 2. The frequency hasn't changed. The number of waves reaching the barrier every second is still the same. And so we're going to rearrange this formula for frequency to show a relationship here. So frequency divided by lambda equals velocity or speed divided by wavelength. Okay, so we know that frequency 1 is equal to frequency 2. And so that means V1 over lambda 1 is equal to V2 over lambda 2. Right? We just made this formula for frequency, speed divided by wavelength. And so if we take frequency number 1, it's the same thing as frequency number 2. So this is frequency number 1, and the same thing would be frequency number 2, just with a different speed and wavelength. So now this is the relationship that we have. On side number 1, the ratio of the speed to the wavelength is equal to the ratio of the speed to the wavelength in the second one. So if the speed goes up by twice as much, the wavelength is going to go up by twice as much, or the other way around. And so we're going to rearrange this just slightly. So we're going to cross multiply, basically. And so we're going to get V2 down here and V1 up here. Okay, and so that's going to be our formula over here. V1 over V2 equals lambda 1 divided by lambda 2, or wavelength 1 divided by wavelength 2. So what this says is that whatever the ratio is for the speeds, it's the same ratio for the wavelengths. So if V1 is twice as big as V2, that means lambda 1 is going to be twice as big as lambda 2. So let's take a look at an example here. A wave has a wavelength of 2 meters in a rare medium. It has a wavelength of 1.5 meters at a speed of 1.2 meters per second in a denser medium to which it transfers. What is the speed of the wave in the rare medium? So we have 4 pieces in this relationship. We have speed 1 and speed 2. We have wavelength 1 and wavelength 2. In any of these problems, it has to give you 3 of those pieces, and you will solve for the 4th. So in the rare medium, that's the first one, it has a wavelength of 2 meters. So this is lambda 1. It has a wavelength of 1.5 meters and a speed of 1.2 meters per second in the denser medium. So that would be lambda 2. And the speed is V2 in the denser medium. And so we're supposed to solve for the speed in the rare medium. And so it goes like this. V1 over V2 is equal to lambda 1 over lambda 2. And we are supposed to solve for the speed in the rare medium. That would be V1. So we need to rearrange this to get V1 by itself. And right now there's just a divided by V2 here, And so if I multiply by V2, I'll have V1 by itself. And so V1 is equal to V1 lambda 1 over lambda 2. Sorry, this is V2. When we solve this, we get 1.2 meters per second times 2 meters divided by 1.5 meters. Okay, and when we solve that, we get V1 is equal to 1.6 meters per second. Now, we should check that this actually makes sense, because we know that when a wave goes from a rare medium into a dense medium, it should slow down and its wavelength should get smaller. So we had a wavelength of 2 meters and it changed to a wavelength of 1.5 meters. So the wavelength got smaller. So it's going into a medium that's more difficult to move. And it should have started faster and went to a slower medium. And in fact, it did. So we got an answer that was faster than the medium it was going to, and so we know that that actually makes sense. And that brings us to Snell's law, or Schnell's law as it actually is. So we said that the speed and wavelength change when a wave moves from one medium to another, but we also said that when it doesn't move head on, when it hits that boundary at an angle, then that angle is going to change too, just like you see when you put a straw inside a glass. So we can also include in the previous relationship that we found the angle as well. So what we get then is the sine of theta 1, or the sine of the incoming angle, the incident angle, divided by the sine of the refracted angle is equal to V1 over V2, which is equal to lambda 1 over lambda 2. So the relationship, the ratio, changes evenly among all of those three things. So the sine of the angle changes with the same ratio as the other two things. So if the speed doubles, so does the sine of the angle. Now, we're not saying that the angle itself doubles. You have to make sure that you're actually using the sine of the angle. Okay? Now, we'll show you what's happening with a few diagrams. So here's a boundary between two mediums. I'm also going to draw in the normal line, which, if you remember, normal just means perpendicular. So the line that is perpendicular to the boundary. So this is the normal. Now we've got a ray coming in like this. And so if this is going from a fast to a slow medium, then the ray is going to bend toward the normal. So the speed is going to decrease, and the wavelength is also going to decrease. And so this ray, we're going to see those two things, and that's going to cause this wave ray to bend toward the normal. Okay, so it's going to be something like this. So it used to be going in at this angle, now it's coming out at this angle. This would be called the incident ray, and this would be called the refracted ray. So let me draw in a couple other things here to hopefully make this a little bit clearer. So we've got wave fronts like this. These are the wave fronts that are traveling in. Remember, the ray just shows you the direction that the waves are traveling. It's just often easier to draw in the wave ray than to draw in all the wave fronts. It just starts looking cluttered. So if the wave fronts are traveling this way, once they reach this boundary, they're going to bend this direction. And they're also going to slow down and lower their wavelength. So they're going to bunch up something like this. I'm going to draw them over here because it's going to make our life a little bit easier a little bit later. So they used to have this wavelength from here to here. Now they have a much smaller wavelength. We also want to draw the angle. So the angle we're talking about, or the angle of incidence, is the angle between the ray and the normal line. That would be this one right over here. So this would be called theta 1, or sometimes theta I, angle of incidence. The angle of refraction is this one right here. That angle is called the angle of refraction, or theta 2. Okay, so notice that the angle is getting smaller, and we're going to need to remember that. So the refracted ray bends toward the normal when it's slowing down, and the angle of incidence, that means, is going to be bigger than the angle of refraction. So we're going to put a greater than symbol in there. And then the wavelength of the refracted wave will be smaller. Or shorter, depends how you like talking about wavelength. Okay, and so what's important here is that everything decreases. When you're going from a fast medium or a rare medium to a dense medium, everything decreases. Okay, the speed decreases, slows down, the wavelength decreases, they get closer together, and the angle decreases, gets smaller. That's the easiest way to think about it. When you're going from a rare to a dense medium, everything gets smaller. Speed, wavelength, and angle. The only thing that doesn't change is the frequency. Let's look at going from slow to fast, or dense to rare. So we've got the incoming ray, or the incident ray, and it's going to hit the barrier over here, and it's going to bend away from the normal. So this is our normal line again. It tells you what perpendicular to the boundary is, and so our wave ray is going to bend away from the normal this time. So let's draw in some wave fronts, and then let's draw in the angle as well. So we're going like this. These are the wave fronts going in. There's more of them, there aren't just 4. And then when they're coming out, they're much longer. Because as it speeds up, we get a longer wavelength. We are also going to have the angle of incidence over here. We're going to call that theta 1. And the angle of refraction is over here, which is theta 2. Now, it looks like, just judging by where I drew these curves, that this curve is bigger than this one, but it's really not. So you can see clearly that this angle is smaller than this angle. This one has bent away from the normal. Okay, and so it's getting larger. Everything is getting larger in this case. So the refracted ray bends away from the normal, which means that theta 1 is less than theta 2, or theta I is less than theta R, incident and refracted. The wavelength is also going to be longer, or larger. And those are the relationships between angle, wavelength, and speed. And in this case, everything increases.